So a metric space X is said to be a second countable space or second axiom space if there exists a countable base for the family of all open subsets of X. Okay. Now, in view of example 3.11, that is to say, in view of this example where we are taking this B, okay, this is the collection of open intervals with endpoints are rational. So this is a countable base for R, and therefore you can see that the collection of all open intervals AB with AB as rational points forms a countable base for the family of all open subsets of R. Hence, the usual metric R is a second countable space. Why? Because from the definition of the second countable space, a metric space X is a second countable if there exists a countable base for the family of all open subsets of X. So here is this set of all real numbers. This set of all real numbers has a countable base of this form. The countable base of this form, and therefore set of all real numbers is a second countable space. Now consider X is equal to Rn, okay, be a metric space with respect to this metric. Then we have seen in the previous example that here is this kind of collection of open balls with center at X and radius R, where R is rational, X is rational. This collection of open spheres forms a countable base for the metric space X is equal to R. It means that X is equal to Rn, okay, has a countable base, and therefore it is a second countable space. So here is this is a second countable space. Okay. In view of this example, here is we have seen that if X is your discrete metric space, then the collection of singletons forms a base for the space X with respect to the discrete metric space. But if X is your countable space, then this collection is a countable base. It means that if X is your discrete metric space and countable, then this family of open sets forms a countable base, and therefore X with this X, a countable set X with discrete metric space is a second countable space. So here is we have this. So discrete metric space X is second countable if X is countable. Now, as I mentioned that what is the first countable? Because we have defined the second countable, so there should be a first countable. So a metric space X is said to be a first countable space or first axiom space if every point X in X there exists a countable family of open sets containing X such that every open set G containing X also contains a member of this family B and X. That is B and X is a subset of G for some n. So here is you can see that a metric space X is said to be a first countable space or first axiom space if every point in X there exists for every point in X there exists a countable family B and X of open sets containing X such that every open set G containing X also contains a member of this family. Now, look the example. The usual metric space is a first countable space. Indeed, we can see that we may take B and X is equal to X minus 1 over n, comma, X plus 1 over n. So this is your open set, okay? This is your open set containing X. So this is the family. So there for each X, so for this X, this is a countable family of open sets containing X, such that every open set containing X, also contains this open interval, and therefore R is a first countable space. The second countable space is also first countable, but the converse is not true. So that is to say, there is a relation between first countable space and second countable space, which is that every second countable space is first countable, but every first countable space need not be a second countable space. Let X be a discrete metric space where X is an uncountable set. Okay? Then we can see that X is first countable but not second countable. As we have seen that if X is a discrete metric space and X is countable, only then it is second countable. But if X is your uncountable, then it is not second countable, but it is a first countable space. How it is first countable space? We can see that for any open sphere, we can take the center at X and radius half is a singleton set X. Okay, why it is singleton X? Because X is a discrete metric space, and therefore this family S 1 over n X and runs from 1 to infinity. This is the collection of countable family of open sets containing X, such that every open set G containing X also contains a member of this family, because the element of this families are the singleton set. Hence, X is a first countable space. Now, if X is uncountable, then the singleton sets are also uncountable. Hence, every base is uncountable. Consequently, X is not second countable when it is uncountable. So, these are two definitions which we have: the first countable space and the second countable space. Now, we have a very general result which says that every metric space X is a first countable space. So from here you can see that whether the metric space is second countable or not, it is a first countable. So of course, since every metric space is first countable, and therefore every second countable space is also first countable space. So here is this is very general that every metric space is a first countable space. Now the proof is very simple. We can say, let's take X is an element and n is any natural number, and set B and X is equal to 1 over n X. Okay, so this is your open sphere with center at X and radius 1 over n. Then B and X, this family is equal to v1x, v1 over 2x, and so on. And this is a countable collection of open subsets of x, such that every member of this collection contains x. Let G be an open set containing x, then there exists S epsilon x such that S epsilon x is a subset of G for some epsilon is greater than 0. And therefore, S n x is equal to 1 over nx is a subset of S epsilon x, and epsilon x is a subset of G for each n is greater than 1 over n. And hence, X is a first countable space. Okay, so in all these lectures, I am already giving you all the several exercises related to the subject which we are considering. So here is a very simple exercise which says that let X be a metric space and Y be a non-empty subset of X. And if XD is second countable, then Y dy is also second countable. And what about the first countable? So if XD is a metric space, Y is a subset of X. Okay, so if XD is first countable, so can we say that Y dy is also first countable? So here is this is given in this exercise. So this is for your exercise. And here we have one more exercise so that you can do by yourself. Okay, now I come to the next section, which is a dense set. As you know that the literary meaning of the dense means very close. Okay, so as I have mentioned in the beginning, the rational numbers and irrational numbers. In the real line, the rational numbers or irrational numbers are placed in a very densely, are placed in densely. That is to say, the distance between the rational number and irrational number is very, very small. Okay, or you can say it is the distance is almost 0. Okay, so you can see that the whole real line is place on the whole real line. We place the rational and irrational numbers very densely, or the rational numbers or irrational numbers are placed very densely, forms a real line. So this phenomena can be extended for a arbitrary set X. But of course, because we are saying that the rational and irrational numbers are placed with 0 distance. So we are using the distance between the two numbers, rational and irrational numbers. So we can define the concept of dense set in a non-empty set X only if we have the idea of the distance over the set X. So for that we need to consider the set X must be metric. That is to say, a non-empty set with a matrix by which we can say that okay, the distance between two elements is this thing. So here is we have the definition. A non-empty subset A of a metric space X is said to be dense or everywhere dense, because everywhere I am using here is in the letter we will use nowhere dense. So sometimes the dense set is also called everywhere dense. But later on we will use only dense. So a non-empty subset A of a metric space X is said to be dense in X. The A is dense in X if the closure of A is equal to X. That is, if every point of X is either a point of A or a limit point of A. So every point of A is either a point of A or a limit point of A. Now, from here you can see that as I'm mentioning about the real line. Okay, so if you consider set of all rational numbers or set of all irrational numbers, so if you consider a set of all rational numbers, then the closure of set of all rational numbers is equal to the whole real line, because the limit points are the irrational numbers. So we are adding rational, we are collecting together rational and irrational numbers, and that forms the whole real line. It means that the Q, the closure of Q is equal to R. So it means what? It means that Q, closure of Q is R. So it is your dense subset of R. So in other words, a set A is dense in X if for every given point X there exists a sequence of points of A such that X converges to X. So a set A is dense in X if for every given point in X there exists a sequence in X that converges to X. It means that the set, it means that the closure of A is equal to X. So now, before giving the example of dense sets, we provide some criterion for being dense. So let X be a non-empty subset of a metric space X. Then the following statements are equivalent. Statement A is for every X, rho XA is equal to 0. That is, the distance from a point X for every point X in X and the set D is equal to 0. So for every point X, the distance between X and A is equal to 0. The closure of A is equal to X, it is already given in the definition of the dense set. So it means that you can say it is a dense set. And A has non-empty intersection with every non-empty open subset of X. Okay. Once again, the proof is very simple. The equivalence of A and B directly follows from theorem this, because we have mentioned that the rho XA is equal to 0 if and only if X is in A and A is your closed set. Okay, so here is from there we can find if and only if X lies in closure of A. So here is this theorem says that you can see that X D be a non-empty X D be a metric space and A be a subset of X, then X belongs to the closure of A if and only if rho of XA is equal to 0. So the A and the equivalence of A and B follows from this theorem. So we prove the equivalence of B and C, equivalence of this and this. Suppose B holds, then we will prove C. So suppose contrary that there exists a non-empty open set O of X such that O intersection A is equal to empty. Now what we have to prove that? We have to prove that A has non-empty intersection with every non-empty open set of X. So we are assuming that there exists a non-empty open set O such that the intersection of this set O with A is empty. So this is empty. Then from here we can see that A lies in the complement of O. Okay, complement of O, and therefore the closure of A is a subset of the closure of complement of O. But the complement of O, because O is open, so the complement of O is closed, and the closure of this set is so it is equal to this because complement of this is closed, and therefore you can see that the closure of A is a subset of the complement of O, where whence the closure of A intersection O is non-empty, and thus A cannot be equal to whole space X, which contradicts to the assumption to this one. It contradicts to this, hence C holds. Now we prove that B implies C implies B. Suppose C holds but B does not. That is, the closure of A is not equal to the whole space. Then we can take the complement of A is not equal to empty set. Okay, and since the closure of A is closed set is a closed set, the complement of this is an open set in X and disjoint from A. So that is means this is the intersection of the closure of A complement intersection A is empty, and since this closure of A complement is your open set, because this set is your closed set, so this is your open set, so open subset of X. So by hypothesis, this intersection is non-empty, which is a contradiction, and therefore we have the closure of A is equal to X. So these are the, you can say, the characterizations of a dense set. So a set is dense if and only if rho XA is equal to 0, or closure of A is equal to X, or A has non-empty intersection with every non-empty open subset of X. Now remark, it can be easily seen that a subset A of X is dense if and only if the complement of A has empty intersection. So here is, we can see that, so here is a set A is dense if and only if the complement of A, this has empty interior, that is to say the interior of this is equal to empty set. So this is true if A is closed, A is dense, if and only if this is true. So here is, we can see that A is dense if and only if the interior of complement of A is an empty set. Now we have the examples. Okay, so we can the set of all rational numbers Q is dense in the usual metric space R, as the closure of Q is equal to R. Now similarly, since the closure of rational numbers is equal to R, okay, so therefore the set of all irrational numbers is dense in the usual metric space R. Now the set A, which consists of A plus IB, is complex numbers. So DA is a subset of complex numbers, where A and B are rationals. Then the closure of A is equal to whole space C, set of all complex number, and therefore A is dense in C. Okay. Similarly, we can see that Qn, which is equal to Q cross Q, where Q is set of all rational numbers. So this is dense in Rn with respect to the usual metric space. Now you can see that under other matrices, whether Qn is a dense set in Rn or not. So here is now I take an example. So set we take X is a set consisting the element X of this form. So X is equal to A1, A2, An, and after An all the entries are 0. but all these A and I's are rational numbers. Okay, so up to n they are non-empty, and after this, from they are they some numbers, but after that all the entries are 0. So this set is dense in LP space with respect to the following, with respect to this metric. Okay, as we have seen that LP space is a metric space with respect to this metric. Now let us see that that is verify. So let's take x is equal to x1, x2 and so on in LP. So this is a sequence in LP space, be an arbitrary element and epsilon be given. Then there exists a positive integer n such that this condition holds good by the definition of LP space. Okay, so this is less than. Now since Q is dense in R, for every real number there is a rational number which is as close to it as we wish. Consequently, we can choose an element y of this form, okay, in A such that this is less than, this term is less than epsilon p by 2. So here is we can take xi, so we can take xi minus ai, so ai from here, okay, and this is less than, because here we are taking all the terms from a1 to an, so from I runs from 1 to n, and this is true for all I runs from n plus 1 to infinity. So from here we can take, and therefore we can see that dpxy whole raised to the power p is equal to this. Okay, by the from here you can get, and this is what? This is equal to, you can take because the rest of the terms. So here is this is this you can break from I runs from 1 to n, then I runs from n plus 1 to infinity. This is less than epsilon p by 2 and this is less than epsilon by p by 2, so the whole is less than epsilon p. It means that dpxy is less than epsilon. It means that the distance from x in LP to A is 0, and therefore from the previous theorem we can say that A is dense in LP space. So here is we have seen that the LP space is a dense, this set, the set A is dense, okay, in LP space, okay, and where the entries here, these are the entries are the rational numbers. Keep in mind, because we will use this factor later. Now we have another example. So let us consider in this example PAB. PAB means a space of all polynomials defined on closed interval AB with rational coefficient. Okay, then the space of all polynomials defined on AB with rational coefficient is dense in CAB. CAB means set of all continuous real valued continuous functions defined on the closed interval AB. To verify this fact, let f be a continuous real valued continuous function defined on AB. Then by Weierstrass theorem, which is mentioned in there exists a sequence Pn of polynomials with real coefficient that converges uniformly to f on AB. That is, for every epsilon positive, there exists a positive integer n such that for all t in AB, in the closed interval AB, the mod of P n t minus f of t is less than epsilon whenever n is greater than capital N. And so d infinity by d infinity P and f is less than epsilon for all n is greater than n. But any polynomial can be uniformly approximated by a polynomial with rational coefficient since Q is dense in R, and therefore corresponding to the sequence Pn, there exists a sequence Qn of polynomials with rational coefficient. That is Qn, the sequence Qn lies in PAB such that the mod of P and T minus Q and T is less than 1 over n. This implies that now you take the supremum, and then from here we can see that d infinity P and Qn is equal to the supremum of this one when supremum over T lies in the closed interval 0, 1, and this is less than 1 over n. And by the triangular inequality, we can have d infinity Fqn is less than or equal to d infinity Fp plus d infinity Pq and Q. This converges to 0 because of this 1 over n, so this converges to 0. Okay, this converges to 0 because of from here, and so the whole thing is converges to 0. It means that Qn converges to 0 and f is your continuous function, and therefore the closure of PAB is equal to CAB. And so PAB of all polynomials defined on AB with rational coefficient is dense in CAB. Now we present another example. So whenever in the metric space, in the course of metric space, whenever you see any example, you must look two important things. What first you see whether the real line with the usual metric satisfies that condition or not. The second is whether a non-empty set with the discrete metric satisfies that condition or not. So whenever you have any definition, any property, or any result in metric spaces, you must look to the set of real numbers with the usual metric and any non-empty set with respect to the discrete metric. You will find some answer from these two spaces. So now next we consider the discrete metric space. So let XD be a discrete metric space. Now since every subset of X is closed, the only dense subset of X is itself. So the discrete no subset of X except itself is a dense set in a discrete metric space. Now by the definition of the completion, every metric space is dense in its completion. Okay. Now suppose we have a sequence of dense open sets. So the first question is the intersection of dense set is dense set, but in general it may not be true. But the intersection of dense open sets in a complete metric space is dense. So we have this result, that is, let Xn be a sequence of dense open sets in a complete metric space X, then the intersection of Gn is also dense in X. To prove this, let X be any open sphere in X. Okay. So S is any open sphere in X. Then in view of the previous result, it is sufficient to show that the intersection of Gn, intersection S, is non-empty. That is to say, we have proved that A is dense in X if and only if A has non-empty intersection with every non-empty open subset of X. So this we prove. So in view of this result, it is sufficient to show that the intersection of Gn intersection S is non-empty, where S is any open sphere in X. Now, since each Gn is dense in X, the closure of Gn is equal to X for all n, and the Gn intersection X is non-empty again by this theorem. So this is non-empty and open in the intersection of two, and open because this is open because this is your open set and this is your open set, and the finite intersection of open set is open set. So this is your open set. So this is non-empty and open set. In particular, G1 intersection X is a non-empty open set, and therefore there exists X1 in G1 intersection X, and R is greater than 0, such that the closed ball SR1 X1 is a subset of SR1 plus epsilon X1 is a subset of G1 intersection G2. That is to say, we can also have here is this is your X1, okay, and then this is your open, this is your closed ball, okay, with radius R1. So this is your closed ball with radius R1. Okay, this always lies, you can extend the radius by epsilon, then the closed ball with center at X1 always lies within an open ball with radius R1 plus epsilon, यानी कि the upper one. So it lies in this one. So here is we have, and this is, and but this is a subset of G1 intersection X for epsilon greater than 0. Similarly, we can take G2 intersection SR1 X1. It is non-empty and open. So we can, there exists X2 in G2 intersection SR1 X1 and R2, with R2 is less than or equal to R1 upon 2, such that this is holds good. Yani ke if you have, this is your X2, here is so you have a, this is your closed ball, okay, and this closed ball lies into G2 intersection XR1 in this one. So it is lies in this one. Continuing this way, we obtain a sequence Xn such that as SRn Xn, the closed ball, is a subset of Gn intersection as open ball as Rn minus 1 Xn minus 1 for all n runs from 1 to infinity, with Rn is less than or equal to Rn minus 1 divided by 2, and which is equal to, you can say that R1 divided by 2 raised to the power n minus 1, and this approaches to 0 as n tends to infinity. And now we can see that whenever m is greater than n, then SR1 X1 contains SR2 X2 and so on and so forth. So this means what? It means that and X is your, so this means that SRX, SRN, XN. So this is a decreasing sequence of non-empty closed subsets of X. And note that X is complete. So this is a decreasing sequence of non-empty closed subset of a complete metric space X, such that the diameter of these closed sets open box converges to 0 as n tends to infinity. And then by using the Cantor intersection theorem, this intersection contains exactly one point, say X. So the X is equal to the intersection of this one. But SRN GXN, this is what? This is a subset of Gn. So the intersection is in the intersection I runs from 1 to infinity Gn. So this lies in G. It means that this intersection is non-empty. So also X is also in S. So it means that X is in this intersection, S is in S, so the intersection of this and S is non-empty, and hence intersection of G and is dense in X. So that is the things. Okay, now I stop over here, and then tomorrow we will discuss the separable metric spaces. Okay, thank you very much.